Hey, thanks everyone for joining. I'll give you a little bit further background or kind of an outline of what we want to cover today. You saw the agenda on the webinar and you've joined, so thank you. But I want to take a closer look at what the additive manufacturing or 3D printing adoption journey looks like in automation, whether you're a machine builder, integrator, or on the manufacturing floor from like a process engineering or manufacturing engineering side of things. Like Jason said, I've been at Extol for 10 years, and my background isn't just 3D printing. I was in the custom design group for automation equipment. So a little bit of unique perspective on 3D printing for the automation factory floor. So when we look at the typical journey for an industrial additive manufacturing application, like I said, whether you're a machine builder, a manufacturer, this is typically what we see, and this really mirrors what Extol's journey was like. Typically, you buy your first benchtop 3D printer, and that can be an FDM or an SLA machine. And we'll talk a little bit about the nuances of different printing technologies here in a bit. But it's typically simple brackets, prototype nesting, physical models. Something has sparked the interest of, hey, there's something with 3D printing. It's valuable. How is it going to fit into our business? And we start small with a benchtop 3D printer. As you start playing around with those simple brackets and those prototype nests and physical models, you start to get mixed results while you're learning, right? You'll have some failures and some parts that the manufacturing process or the printer itself just doesn't quite fit, and others it's like, oh, there's something here, and you kind of grow those applications. When we were at this point, we had a larger scale machine that we wanted to put 100 plus printed nests. So you can kind of see the machine in the background there in the middle and a close-up of one of the nests. Those were all FDM printed nests. And we had two printers, benchtop printers, Markforged, that were going for 30 days, pretty much 24/7 to be able to print that whole thing. So on a smaller mid scale, yeah, maybe you can keep up, but all of a sudden it starts to get to the point of it's extensive project management to keep that printer full, and it just takes a long time. And that's really where we start to see the benefits of an industrial additive manufacturing solution beyond the benchtop. In this case, we'll be talking about the HP multi-jet fusion technology, where quality and scale can go to the next level. You're starting to do more production fixtures that are more robust and very close, if not better, than CNC'd alternatives. You get into complex end-of-arm tools, complex details. We've seen once you get to this point, the adoption can grow by over 10 times, right? Where you're, like I said, you're able to display significant CNC machining and poured urethane. So we'll touch a little bit more. And with that, you're either going to develop a partner that has access to this industrial AM technology or additive manufacturing, like Extol or like other suppliers that have these printers, or you can bring it in house yourself. Typically what we see is it makes more sense at that early phase to have a great partner. When you talk about scale, right? I wanted to give you kind of a quote from one of our customers, and we see this frequently, where MJF 3D printing has a quick turnaround time. It's never delayed by raw materials, and the cost is similar or better than CNC machining. And this automation company is, and we have multiple, have displaced 200,000 plus dollars worth of CNC machine details that would have typically been poured urethane, CNC Delrin, CNC aluminum, those type of materials. And what you're seeing here in the left-hand side is really 3 or 4 printed nests and you can barely see where they are, which is kind of our goal, right? So you have one here, you've got one back here, one here, but it's so integrated into an industrial fixture or custom automated machine that it looks like it fits, and we want it to fade into the background because it is an industrial solution that doesn't stick out like a sore thumb like some printing technologies may. So you may ask, where do we find the value of additive manufacturing automation? And the three areas that we see the biggest benefits would be dependable lead times, where for printing we could be in the 5 to 10 business days versus maybe 4 to 6 weeks if you're outsourcing CNC. Different if you have internal CNC, it's a different kind of advantage there. Design freedom. When we see low to medium complexity details, it's similar to CNC cost. If we see high complexity details, it's less than CNC cost, outsourced CNC cost. And then soft touch and non-marking materials, being able to replace machine plastics or poured urethane with a printed TPU. And as a reminder, for those that have joined in, if you have questions throughout, just feel free to drop them in the chat. We're monitoring that, and we'd love to answer as we go along. So there's a lot of different 3D printing technologies, and we're not here to kind of split hairs on all of them, right? But when I think about the largest majority of 3D printing technologies that are used in automation, there's really three. There's FDM, or fused deposition modeling. Think of that as a building up layer by layer with a heated plastic going through a hot end. And that's typically what people think about when they think about benchtop or at-home 3D printing. You can see the layer lines, and it's just building with melted plastic and extruding each point of the part. Then there's SLA. That's more of a resin-based technology, thermal set plastic versus thermal plastic. So it's UV cured, it's an engineered resin. It's not something that you can melt or reshape after it's printed. And then multi-jet fusion, powder-based, and I've actually got a video that we'll play here shortly that kind of runs through what that industrial 3D printing looks like. And then I've got metals on there. A lot of people talk about metals in automation and like, how could we use 3D printed metals? This is going to be the next big thing. I don't see it quite yet because a lot of the things that people are looking for are simple hex posts or simple little details that the cost of the machine just doesn't justify it. So here's a quick video on the HP Multi-Jet Fusion 3D printing process.
HP Multi-Jet Fusion is a powder-based 3D printing process unlocking new efficiencies geared towards enabling production. Let's take a closer look at the printing process from start to finish. The process starts by evaluating each part and selecting the optimal print orientation. The parts are then placed in the build envelope. Special care is made to balance height and pack density while avoiding sudden changes in printed surface area. Parts are nested in 3D space within the print envelope, which is approximately 15 by 11 by 15 inches. Once the build is packed, it is sent to the printer. The build unit is inserted into the processing station to be filled with powder. The station automatically fills the build unit with the desired ratio of recycled and new material. Typically, the mixed ratio is 80% recycled and 20% new. The Multi-Jet Fusion printing process uses the highest percentage of recycled material of any 3D printing process. Once filled, the build unit is inserted into the printer and the printing process is initiated. The parts are grown layer by layer, 80 microns at a time. There are 4 steps to the HP multi-jet fusion printing process. First, powder is spread across the build area. Next, fusing and detailing agents are jetted onto the powder. These aren't binders, rather, they respond to IR energy. The fusing agent absorbs IR energy and causes the powder to get hot, while the detailing agent evaporates, causing the powder to cool. This causes a sharp temperature transition, which results in a fused part with distinct, precise edges. Multi-jet fusion parts are stronger than those printed with SLS and other technologies due to greater energy exposure. On each pass, energy is absorbed multiple layers deep, creating strength in every direction. Once the printing is complete, the build unit is removed and the cooling process begins. Builds can be naturally cooled or fast cooled in the processing station. A full build naturally cools in about 24 hours. And then is ready for unpacking. First, the build unit is inserted into the processing station and the archaeological dig begins. Unfused powder is vacuumed away and reclaimed for future builds. Parts are extracted and excess powder is removed. The final step is media blasting to strip the remaining unfused powder. Depending on part size and geometry, this can be automated or done by hand. The parts get a final blow-off and are ready to be used for functional prototypes, tooling, or production applications.
So that will jump right into a comparison of the 3 different printing technologies that we talked about earlier. Kind of go from the top down, but polymer type, we talked about that. Thermoplastic is really cool from being able to remelt and be able to utilize the parts in a more functional way. Dimensional resolution. MJF and FDM are relatively similar depending on the geometries. SLA is a little bit higher resolution capability. Same with the surface smoothness, right? SLA is going to be your smoothest, but the downside to SLA with those 2 benefits is it's super brittle and it can break if you look at it sometimes. From a break along the layer lines, that's a huge thing from the FDM side where we see failures in automation early on in your trials or your journey where it will break along those Z-height layers. The multi-jet fusion, as we saw in the video, the energy is penetrating multiple layers deep, giving you micro welds between each layer, so you get closer isotropic strength. And then when you look at air and water tight right out of the printer, MJF and SLA are air and water tight, but FDM is way more porous because of those layer lines. And then part quantity and speed. This is where when we talk about industrial solutions, HP multi-jet fusion is going to be the fastest for many parts at one time. So all of these things are things to consider when you're asking for 3D printed fixtures by your suppliers. If you don't specify one of these, you could get any of them. So make sure you're getting an industrial solution, and we'd love to help you figure out how best to use multi-jet fusion in your machines. Now, I want to shift more into use cases, right? So we've kind of laid the groundwork of the journey and the technology. Now let's give you some examples, things to chew on of different really good applications for printing and automation and industrial. So we're going to first look at rigid fixtures, have an example of those, complex geometries, soft touch fixtures, and then we'll touch on printing parts for debugging machines. So the first rigid validation fixtures. This was one of our customers that replaced replaced aluminum fixtures with PA12 for extreme environmental testing conditions. It ended up being about half the time and less cost than the CNC aluminum fixture alternative. So that's a really big thing that we get a lot is, well, it's always been aluminum or plastic's not strong enough. But a lot of times the plastic can be just strong enough, right? Or as well as lighter. So Marcia had a question in the comments. Yeah, there will be a time for questions, but if you have a specific question as I'm going, feel free to put it in the chat and we'll answer it as we go.
Give us your questions now.
Yes. Start typing, Marshall. So the other thing that we get a lot of is it strong enough? And so the next video here is to kind of have a fun example of what these printed fixtures can hold up to. You know, Jason and I both had quite a bit of fun videoing that.
Mm-hmm. You see the question from David?
Yes, I do see that. So there's three main polymers that we have for the multi-jet fusion in-house at Extol. We have a nylon 12, a TPU from BASF, and a polypropylene. For multi-jet fusion, there are also others, PA11, PA12 glass bead, some TPAs, different TPUs, but we find that the three that we have, the nylon 12, TPU, and polypropylene, fit most applications. Great question, and thanks Chris for the shout out there. It was a
designers who has
yes, one of our custom equipment designers. That's his truck. So here's a little more detailed example of 3D CNC details that were displaced at scale. This was a robot cell that we had 150 total components that resulted in 98 unique designs, so not a lot of quantity of each individual component. And when you compare traditional manufacturing to multi-jet fusion printing, you can see that the lead time, there was a great reduction there. Cost was substantial when it came to a project this size and mix of components and complexity of some of the components. And then design freedom was definitely very high with being able to print it. So we can also see that utilizing 3D printing in specific areas where it makes the most sense or adds the most value can be a huge benefit. So you can see here, this end of arm had about 15 different axes of holes, right, for attachment of these metal grippers. So more detail in the gripper, more like repeatable, dimensionally stable, different things like that that were needed for that specific interface. But then taking that really complex machine part and turning it into a 3D printed part was a huge benefit there. And then you can see all of these printed nest blocks down here, which were a great weight saving because these were interchangeable nesting plates that the operator or maintenance would be moving around. So the next kind of group of applications I want to touch on is complex geometries. So you can see here multi setups in a 3D CNC or a CNC operation, or 5-axis, or not even machinable, right? So whether it's integrating sensors and passageways into the parts, whether it's specific air cooling properties to be able to shroud an ultrasonic horn, or an end of arm tool that has the vacuum lines integrated right into the printed component. This was actually the machine fixture that we showed on the title slide. But this is an example of a full machine fixture package. You can see there was 28 details. None were identical, so each unique. You can see that they were nested in 3 different MJF builds. So you can kind of see the packs up at the top right here. But really the benefits for this, right? We had complex geometry. We had threaded inserts that were able to aid in mounting sensors and clamps and different things like that. And then it's a high mix, but low quantity of each individual. So it would, be higher time for CNC programming and different things like that of programming for just one detail of each style. And something like this might cost, around $7,000 from a package standpoint. So very, very similar to a CNC package there. Like I mentioned, right, threaded inserts. So whether it's a helicoil on the right or a heated brass insert on the left, we're finding that those are ways that our builders are attaching clamps and sensors and different things like that to printed material. Or
you can print threads that are large as well, right?
Yeah, that's a great point. So actually on the left-hand side here, this is a printed in thread. It works lower torque, and if you want to take the screw in and out several times, it has the same kind of limitations as if you were to just tap a standard plastic part, right?
Yeah.
But definitely feasible. And then you can do self-tapping screws. You can do all sorts of things. But from a machine build side or custom automation, we typically see like a brass insert. And that's something that we can help you with and provide in the printed part when it shows up at your facility. We could have those installed for you. The other thing that's unique about MJF over other printing technologies is the robustness, being able to machine, whether it's reaming out a dowel hole or just decking off the surface, different things like that. Definitely feasible. So yeah, so Josh had a quick question on if we work on the design for an end of arm, do we get the STL file also? Typically, we're helping our customers like with the design from a consultative approach, but we do also have CAD resources, and yeah, step file STL, that would be the output. If you have a design that you're designing and you want us to print, step file or STL would be what we'd want to start the conversation with. That's a really good question too on the printable thread size. I would say that it's in the M6 to M8 range. If you go any smaller than that, you're probably just going to be you're going to have to chase the printed threads with a tap anyway. So I would go with printing the tap drill size and just adding the threads afterwards.
I have a question about machining. is one of the benefits of that the ability to print a fixture, and then when you actually get real parts that are going to go into the fixture, you can then machine it and tune it to those parts, the real parts, as opposed to, because nothing ever lines up exactly.
Yep, that can definitely be a benefit there. Whether it's, or if you need a sealing surface on a detail, right? And the printed texture is just not quite smooth enough. We've done that where we machine just, half a millimeter off just to get to a nice smooth surface. So rework would be, the message here is if your machine builders need to make a change to a printed part, it's a possibility. Yep.
Got it.
And then soft touch tooling, we touched on this. This is the picture of the machine earlier in the presentation, but this is where we're using BSF TPU to prevent marking on an A surface. So assembly fixtures, end of arm tooling, and then it's a poured urethane alternative. We'll talk a little bit more about that, like the design requirements or the design thought later. But like this one is a TPU on top of an aluminum base. These are TPU blocks that are on hex post risers, and then this is just a plain TPU part.
What are the general tolerances for linear and contours?
Yeah, so I like to start with PA12 is like plus minus 0.25 millimeters, so around 8/1000 of an inch. And then it scales depending on the size of the part. There's different things that we can take into consideration: part orientation within the print bed, how we design the part to open up the tolerance acceptability of how the fixture is designed, or do we integrate machine details where the tolerance is really critical and we use the printed detail for larger contours or trickier to machine things that aren't as critical in tolerance. So that'd be where we'd start. Yep. And I've seen it better, and I've seen it XYZ. So XY is the most accurate because that's how the fusing and detailing agent are being spread. The Z height is a little bit higher tolerance. Yeah, that's a great one, Doug. I learned additive on a Mark Forged Onyx. I will say that if you're starting to do like carbon fiber and fiberglass inlays on a Mark Forged, you can get really, really stiff and really, really strong. But from just an Onyx to a PA12, your layer lines are really where it opens up, right? You can have smaller details on your fixture that won't break off when hit, because you've got a more stout adhesion between layers. Great comment there. So yeah, this would be that soft touch tooling package that we talked about. So you can see that in the build on the left hand side. 4 different nests, honeycombed and vapor smooth. So we'll touch on those specific things in a second here. And then, like mentioned earlier, from a custom grippers or gripper fingers from end of arms, so complexity unlocked. If you need more stiffness, you could couple the TPU with PA12 like you see on the bottom there, or just have a TPU like you have on the top there. And then just real quick, I want to touch on parts for machine debug. We see a lot of machine integrators or manufacturers that have a delayed injection mold tool, and they can't set up their manufacturing cell or their fixtures without some sort of part to get them close. And so in this case, we were prototyping a part for a customer to be able to validate their welding fixture. And on the next slide, we can see that the printed parts were actually able to be welded because they're thermoplastic. So This is a vibe welder with our printed parts. So that, yeah, so that was a nylon 12 that was just welded there. So for vibe, nylon 12 works well. Spin welding, it works well. Laser welding from like a direct laser welding, you could use that. And then for like hot plate, we typically use the polypropylene for like reservoirs and different things like that. And we have a resident expert of the shop that was just shown here in the chat. That's awesome. So some really high level things to think about from a design and best practices. I'd be happy to go into any of these way deeper one-on-one with you guys if you have specific applications you want to talk through. But I'm going to go through these pretty quick. This PowerPoint will be available on the recording if you want to dive in deeper. So when we talk about 3D printing, we want to talk about optimizing fixture size. When you have a manufacturing process where you're putting material only where it's needed, you also want to think about that in your fixture design versus limiting the amount of details. You want to limit where you're supporting to just enough, right? So with that, you can minimize the cost by having smaller to medium size details that can nest better in a MJF build. Support only where you need it. Better printer efficiencies like we talked about. And then it also gives you flexibility from not having a detail that's, or a part that's landlocked in a few large fixtures that are supporting it from multiple angles at the same time. When we talk about cost optimization, this is similar to those same lines. When you think about the analogy of how you fit the most material into a jar between rocks, stones, and sand, right? We want to do the same thing with the printing envelope. So for something like this was that large robot cell that had 150 components on it. We started with a large part, and then we sprinkled in some pebbles or stones, and then we added sand, right? And so this was able to spread the cost over a lot of different details. Maybe that large detail would have been more cost effective by itself to be machined, but with the whole package was way less when looking at costs. The other thing to think about is honeycombing. So there's a thing called pack density. So how much surface area is being fused at the same time on one single layer. So for this bulky block here, you can see that you can physically fit two parts on a single layer, but the pack density is too high. It's in the 30% range. We want to be in the 8 to 12% for a good process window for these printers. So it's not feasible as shown. So if we want them solid, we have to increase the height. Well, increasing the height also increases the cost because of how long it is in the printer is the greatest cost driver. So all of a sudden, your current nesting density on this middle example is around 14%, which it's feasible, but you've got a cost increase. We'd be looking at, say, $1,250 a part in this example here. As soon as you do honeycombing, so you can see the internal honeycombing here, typically we don't have it exposed and we just trap the unfused powder in those internal channels. But as soon as you honeycomb it, the density goes way down and you can put it back on the same layers as you had in the very first place, and now it is printable. And you've more than halved the cost of the parts because you just honeycombed it. So that's a service that Extol provides. We have a software that honeycombs that, so you could just give us the solid model, and we could walk through what settings we'd want to use together for your specific application to make it most cost effective. When we talk about the soft touch tooling, there's two different methodologies there. There's a TPU cap design, so whether you're printing a PA12 base and a TPU cap, so it basically allows for changeover. It does increase the design time a little bit, right? Because you're splitting and you've got that joint to design. But it gives you the ability to have a stiffer fixture if you have a really tall fixture, and putting the money or the expense of the TPU a little bit premium material than the PA12 only where the value is touching the customer part. Or you can go the full TPU route. It gives you simplicity in assembly, simplicity in design. This works well for shorter fixtures that don't have a lot of Z height to make up with a different material. And then if you had lower force requirements. Yes, we have used this as for sonic welding. We have a customer that does a 4mm cap as the TPU with a hard PA12 base on it. So so in that case, we want to increase the rigidity of the nest so that the sonic welding doesn't dissipate the energy too much in the TPU, but it works out great. That's an interesting note from Jason about pricing in Europe there. And then so the vapor smoothing process, it's a chemical smoothing post process that takes the TPU and PA12 from this gray texture and color to a more nitrile rubber in the TPU side of things. So it gives you the benefit of cleaning your nest easier. It doesn't allow for collecting debris in some of the crevices of that outer surface roughness of the printed material. And it's a great non-marking attribute there. From a vapor smoothing consideration, right? We're hanging the parts if we're vapor smoothing or setting them on a wire mesh. So knowing where we can hang them, whether we add a hole or a loop to hang the parts, or just setting them on the wire mesh on a non-critical surface. So this would just be like the mounting surface of a fixture. And with that, just a few more best practices. Add radii wherever possible, avoiding sharp corners. That's the biggest benefit of additive. And when you're trying to reduce the ability for marking, the bigger the radii, the less that your parts are going to get marked in the fixture. From a labeling standpoint, part labeling, we can also do that as a service, but we typically use Arial Bold around 1/4 of an inch or 6mm height font size, and then about 0.75 millimeters or 30/1000ths of an inch extruded or debossed or embossed into the part. Yes, you can add one yourself, Jason. Go ahead and put it in the comments and I'll read it for you. And then standard honeycombing, those are some things that we think about. And consult Extol on an application before or during design to ensure the best results.
If a large part fails during print, are we charged for the extra reprint time?
So that would be a no. If it's something would be on like the design side or different things like that, and it breaks after printing, that might be a different story. But if the print bed fails, that would be on us, and we keep these things humming. So yeah, no, that's a great one. Jason adding texture wherever possible. It kind of hides some imperfections. And I see that a lot more in like consumer product with printing, where from a fixture side of things, typically we're either vapor smoothing it, or it's an industrial setting where people aren't too worried about the surface look. But that's a great point there.
Mm-hmm.
So with that, I'm going to turn it over to Jason. He's going to give a quick overview of Extol. But if you have any questions or you have an application, just know that you can reach out to me, Jason. The website has a way to upload parts or to get in contact with us. And we're here to support. We've got 3 MJF machines that we utilize to help our customers with manufacturing of their printed fixtures.
Yeah, and keep the comments and questions rolling in. This has been really good. I wanted to take a moment to explain how 3D printing fits in with the other things that Extol does. At Extol, we solve complex plastic manufacturing challenges. That's our strategy, and it's actually depicted in our logo. The square cross portion of our logo actually shows this graphic. There's people and companies with plastic welding expertise on one side of the chart, and then there's others that have custom automation expertise on the other. The issue that we find is plastic welding providers don't do very well with custom solutions. They basically make a box like a standard machine, and hopefully your application fits within it. On the other side, we have custom machine builders that lack plastic welding expertise. They can craft a solution around your application, but they don't have the plastic expertise to make it a high-performing, optimized solution. Extol is the best of both. You get a configurable plastic welding solution that's optimized for performance, because we have both the plastic welding expertise and the custom automation expertise. And that splits out in 3 different ways: engineering services, plastic assembly technologies, and custom automation. 3D printing, we can classify that as an engineering service. You can get 3D printed parts, you can get 3D printed fixtures, you can get prototypes, you can get production parts. Our lab, we help you with development of your applications, and we'll do some prototyping for you, run trials to help you validate your application, your part design, your manufacturing solution. We can help you with all of that. You can see there's a bunch of different plastic assembly technologies that we offer, and we will build into a machine, or we will sell to your own preferred machine builder, and they can integrate it into some equipment. And then lastly, we supply custom automation, whether that's a fully automated line that nobody ever touches a part, semi-automated, standalone, kind of everything in between. And then, of course, those integration packages that can be integrated by any other machine builder. We partner with you throughout your project lifecycle. So when you're in the development stages, we help you with manufacturing concepts, and we develop an efficient and robust manufacturing process that will work for an optimized solution. We help you design your weld joints and 3D print in samples. We also help you prove out your processes with trials, which gives you confidence that you're going to be ready for production. Then when you're ready to move to validation, we print those parts and can help you with prototyping. We can help you with building parts to fulfill early production quantities. And when you're ready for getting equipment, our innovative plastic assembly technologies are at your disposal. If you're already working with a machine builder, we offer integration packages. And of course, you can press the easy button and just get your whole assembly solution from us. We customize your equipment to meet your exact needs. Whether you need standalone machines, interchangeable fixtures, or fully automated assembly lines, we've got you covered. And then when you hit production, we install the equipment and support you. You can have us help you with preventative maintenance, spare parts, troubleshooting, repairs. We get feedback all the time that says our service and our support is excellent. And if you need to make updates and process improvements, we can, of course, help you with that. We also have, we can do some contract manufacturing if you've got some low volumes. And then finally, as your project phases out of production, then we can help you retrofit your machine or build new tooling for your next project. We also refurbish equipment and make it like new again, so that you can have many, many more years of service with whatever capital that you've purchased. I'm curious to know, does this life cycle replicate what you're used to? Is there anything that we miss, any steps along the way that aren't included there, just let us know in the chat. I'm curious to know. While you guys are thinking of other questions, I'm going to throw this up here. This is Andrew's contact information. He's on LinkedIn, and you can send him an email. You can give him a phone call. David has the question, how does MJF part density compare to solid plastic parts?
Yeah, that's a great question. Typically, I would say it's around like 99.8%. If you're printing it solid, right? There's going to be a little bit of the fusing agent or the carbon black in it. We have seen, and it really depends to how the plastic is manufactured, right? So when we're comparing a injection molded brake reservoir versus a 3D printed brake reservoir that is identical geometry, just printed versus injection molded, we see about a 70, like the printed part is about 75% of the total strength or burst pressure. And the main difference is there we don't have pressure in the printing process that you do have in the injection molding.
Yeah,
so
sort of pack pressure. Yeah.
Yep. So those would be kind of the two insights I would say to kind of address that question.
I have a question. So this fixture that's in this video,
Yep.
was that honeycombed or solid?
No, that was honeycomb. So that had a 3 millimeter outer wall with 2 millimeter honeycomb structures that were about 20 millimeter size honeycomb or hexagons. Yep.
Oh, okay, nice.
So that is a honeycomb fixture.
Chris Ferris says, nice job, guys. Thank you.
Yeah, appreciate it.
What were you going to say, Andrew?
Oh, I was just going to say, and that's with the trapped unfused powder in the part itself.
Oh, right. Yeah, the bottom's closed up.
Yep. So it's a 3 millimeter outer wall all the way around.
Mm-hmm. Alicia says, thanks for all the information provided. You're welcome, Alicia. You guys will all receive a email with the recording and then a PDF of all these slides. So you'll be able to access that afterwards. And then I think there's probably a lot of people that signed up who didn't actually join us live, but that's totally okay because they know that they can get the content after the fact.
Yeah, and for all of the videos that aren't in the PDF, our YouTube channel has, I believe, all of the videos that were presented here today. So if you want to reference a video and you don't want to go through the whole webinar to find it, that's a great resource as well.
Yep, that's one way to do it. I typically, when I publish the video, YouTube has those chapter functions.
Oh yeah.
So you can actually in the webinar, you can find the spot where you want to be, and I'll probably call out those videos so they're easy to find in there too.
Well, that's even better. High class. I like it.
I do it again. Or maybe I'll link the videos, the raw videos from YouTube in the email that I sent. I haven't decided yet. Maybe all three. Any other questions? If not, we're going to wrap this thing up and let you guys get on with your day.
I will say that Jason called me a 3D printing nerd. I'll call Jason a marketing content nerd.
Yes. I'll own it. Yeah. Great. Well, thanks everybody for joining. If you have any other questions after we close this thing out, please feel free to either reply to the email that you get with follow-up or just send Andrew a message right away. I'll put that right back up on the screen so you can take a screenshot, write it down, whatever you want to do, and we'll be following up with you so shortly.
Real
thanks,
quick,
everybody.
Josh had a build plate question.
Yes.
15 by 11 by 15 inches is the print envelope. So,
but by no means does that mean you can't print larger parts.
That's right. We've printed an 11-foot long part, or 11 foot. 11 feet by 5 feet is the biggest part to date that we printed, and we were within 2 millimeters. So, good stuff.
Pretty good. It's pretty good. All right.
Have a great day, everyone.
See you later.